Hello, everyone. I'm talking about the controls project that we're doing, that I was working on. So for this project, I was working task-based modeling the MK7 hydraulic arresting system for the newer aircraft carriers to basically model this arresting system that would bring the plane to a halt on the runway as the plane lands. So we have this mass moving carriage, we have this energy mass over piston, we have the spring constant, we have these two springs, and then we have these initial conditions. Another initial condition that we have to take into account is the fact that the plane lands at 64 meters per second. And our constraint is also that it also must come to a complete stop within 2,500 meters. And the number of G's the pilot experiences during landing should be minimized for safety. So, and we have to finding a KD ratio that helps us achieve all these goals. The KD ratio is basically, the KD constant is basically a damping ratio for these mass piston energy absorbers. So my objective was to make sure that the plane lands within as short distance as possible, whilst minimizing the G-force and meeting the constraints of 2,500 meters. So I initially started off with a transfer function between masses of 2 and 3, and then masses 1 and 2, and then connecting them with mass 1 and 3. But I ran into some issues with that and realized that I had some sign convention errors, and going back and fixing it would take a lot of work. Instead, I adopted a state space model, which is represented by my MATLAB code, which is here. As you can see, the A matrix is represented like this, with the first three rows being, with these three rows showing, with these three basically showing like the x1 dots, x2 dots, and x3 dots. And these are showing the effects of the spring systems and the mass temper and the masses on the springs. Our B matrix is 0 since we didn't have any external forces to take into account. Our C matrix is 1, 5 zeros because we're only worrying about the displace. We're only worrying about how far the plane travels along the runway. And our D matrix is 0 and our initial condition is 0 for everything except the plane landing velocity, which is V naught, which is 64 meters per second for the aircraft, and our aircraft can mass 20,000. And basically what I did was that I took this model, I took this state space function, and I put it into Simulink like this. And Simulink filled all these parameters in. And then I had a scope connected to this state space function, meaning that this scope would show the displacement. I took the derivative of the displacement, defined the velocity. I took the derivative of the velocity, defined the acceleration. And then I divided the acceleration by 9.81 to see how my G-force was acting on the pilot as the landings happen. So looking at our slides, we can see that when we achieve the best results when a KD value is 1,500, the furthest a pilot goes along the runway is 634 meters, which is significantly below our 2,500 meter threshold. And the pilot comes to stop around a distance of 600 meters, which is, as mentioned, less. There is a degree of overshoot, but as the pilot overshoots, the control system counters for the system is designed so that it counters for that overshoot as soon as possible, which is why we don't see a lot of overshoot happening. If we look at the velocity of the aircraft, a similar we see that it starts off at 64, it goes down at a pretty quick pace. And pretty much we can see that by like 10 seconds, it's almost hovering less than 10 meters per second. It goes a little bit below, it goes basically a little bit in the opposite direction, and then which is the result of the overshooting displacement. And then it basically goes up to 0, which is only 1. With acceleration and G-forces, these quantities are related to each other. I basically have them on the same acceleration, same graph. As you can see from this graph, that the maximum load that a pilot faces is 0.75, which is pretty low considering the fact that the average that the average human can stand up to 2 to 4, maybe even 6 G's worth of accelerated gravitational G-forces. For the second part of the question, we were using the same system. The Navy would like to use the same system to land a 550 kilogram UAV, which would land with a speed of 35 meters per second. So the damping ratio stays the same. Everything stays the same, except I change this mass 1 to be 550 and this V0 to be 35. And then I run this code again. I go into my Simulink, and then I look at all these graphs. So if you look at these graphs here, we can see that the drone doesn't follow the same pattern as the aircraft, because the aircraft, as we saw, that it was more or less flattening out as we got further, but the drone is oscillating more. The drone is oscillating more. It means that it's behaving like a mass spring inside of a car, which is not very good, which could mean that there's damage being caused to the equipment. It should be mentioned that maybe because of this effect happening, the Navy might want to consider switching to a system that has lower damping, since both the mass and the velocity are lower, because at the KD of 1500, there's a lot of force being exerted, which is causing the drone to basically oscillate like a mass and a spring system. Similar pattern happens with the drone velocity, where we start off at 64 and then we go down pretty drastically, and then we come to a stop in a shorter amount of time. But it follows a pattern from the position, which is something that we don't want. We want to get something like this. Basically means that it steadily declines and comes to zero instead of this oscillatory pattern happening. If we look at the acceleration, we can see that the maximum g-force is a much higher, 3.4 compared to the 0.75 that the aircraft faced, which means that there is more force being applied as mentioned prior. So their damping ratio should be considered to be lowered. For the last part of this project, we're talking about advanced terrestrial gear systems, which basically involves using water spinners and drums. There's 2 drums, so the area is 20 meters per second since each is 10. Viscosity of the water, which we use the MATLAB code here, we updated it, which is this. And then we can find, since we know the KD, we can find these informations to find the length, because now the KD ratio, the KD constant is being replaced by mu A over L. And for the drone, a safe value is 300 kilograms per second, kilogram. Like a 300 safe KD value is 300, which at 300 we will see that a similar pattern happens. That the drone position and the acceleration and the velocity similar to the aircraft, which is what we're after. So to get that KD ratio, we need a value of we need a distance or L value of 6.667 times 10 to the power -5. And then as we know, the aircraft is fine with 1500 KD value. So we can just, insert the A's and the mu's and the KD and the L and the KD, and we can use that to find L, which is basically what I did in this part of the MATLAB code. So overall, that's that overall, we should consider, like, when we design these systems for terrestrial gears, we don't want to exert too much force, so we should consider how heavy the plane or the drone being landed is and how fast it lands, and we should determine our KD value appropriately and design our systems according to that. Thank you.